Is there individual classes? Like if you're not available,
What do you mean?
if you're sick or something, can you just connect it with a Zoom meeting?
If you're sick and you're at home, you can connect and watch class with everybody else. Or you can just watch it later.
Okay. We got the luckiest idea. We just found a monkey on the ground.
Oh, yeah.
The
one outside?
Yeah.
Sharpener isn't working.
And it actually really helps.
Yep.
Where's Ozzy?
He's in eighth grade right now.
Oh, he's tired.
Yeah.
Basically the same as the next case. There's gonna be I plus K plus infinity. This is on the I.
Is our lab today the Rube Goldberg?
Yep.
The last two lessons.
Oh,
this
one month.
Just gonna wrap it up.
Today is actually a subject, right? Subject in that, we have a concrete verb. This one always remains present. One. So like how they have here, it has 1 month travel, or it is necessary to work. You would say, I did trabajar, or I did trabajar. No. No. Maybe after class, yeah. I think about the So, notice that the subject on the next one, because we make it like this. Juan tiene un examen mañana, pero tiene que estudiar. There we go. There's a subject, right? The subject is long. I'm sure you have to, there's no subject. So, aprender matemáticas es difícil. Hay que estudiar. Okay, you ready? Yeah.
I think someone's here.
Probably.
I heard the door swing open.
English. Not English. You have all the connotations. Okay, I can make P in that ciudad. So, not me, and not me, yeah. Or you can say one must live in the city, or it is necessary to live in the city. I always put one must live in the city. Yeah, there you go. So, interchangeably, right?
Is that solves? Who solves this? And how?
I don't know who did that one. I think DJ.
How does she do it?
Wow, she's good.
I think Bailey taught her this. Yes, someone's here. Danny.
Yeah.
My favorite TV show that I've been watching since I was little just insulted me last night. They had a filler episode right before the season finale.
Uh-oh. That's never good. That's cheap.
I know.
What show is this?
NCIS.
Oh, good show.
And they only had 10 episodes this year
Yeah,
or this season.
yeah.
And they just had their 100th their 1000th episode
Yeah.
across all the
Did they really? 1,000?
across all of the spin-offs, of course.
Right.
But then it was a filler too for the 1000th episode.
Man, that's cheap. That's just cheap. They shouldn't do that.
I mean, even with Jimmy and Jessica's relationship, doing something with that, it's an easy thing. And I would be happy.
The writers are copping out on you, huh? That's not cool.
Not cool at all.
Not cool at all. Next week.
What lesson is this?
31, my dear. We're nearly done.
Yay! Is the final exam going to be tougher than the midterm?
If you can do the slideshow
I need to study.
and you can do Jeopardy,
I
you'll be fine.
My favorite is doing the slideshow
Yeah.
because I wouldn't say it's easy, but it does make it. You have to do everything, and it's kind of like
Mhm.
flashcards almost.
Yep.
You run through it a couple times and you do it, and
I just revised through the whole book for midterm,
Good.
and then I got 101.
Well, there's a lot of material this year, so there's a bonus. There's actually, it's a two options for a bonus. You can do two different things. There's one of them's a 2-point, one of them's a 3-point to give you a total of 5 points. So one's a question, and the other is what you call a lab practical, which means you actually are going to look at either something or some phenomenon, and you need to tell me what it is and how it's going on. You need to analyze it for me. And if you can do that, you'll be all set.
I would have got a 96 without those bonus.
Emma is annoyed.
I am. Yes, I'm annoyed.
That is so cheap. I don't blame you. I get annoyed too.
No, I'm disgusted.
Disgusted. I love it.
A great episode before their season finale. Like the
Mhm.
time when Ziva came back, they were building through that all season. And this year they have the this season. They have the relationship between Jessica Knight and Jimmy Palmer. They can easily put that in episodes. It's not that hard, but they didn't.
Yeah, yeah, I didn't like, there's a couple shows that I really love where the finale kind of let me down. Like Breaking Bad, I thought the finale was kind of bleh. It was over the top and unnecessary. That didn't make it for me. But
Stereo unit 8 test or just final exam?
it's all part of the Mhm.
What didn't let me down at season finale wise and filler episodes wise was DuckTales.
DuckTales.
A great.
I
season
forgot
finale.
about DuckTales.
They were building up to the
Hey,
season
y'all.
finale all season. Fail me, DuckTales did not. And this is DuckTales is a kid show.
It's cute
Instead
too.
of Tell itself. I don't do words. Anyway, they should have a higher standard for themselves when it's considering when the season finale is coming up. Especially when NCIS had a two-parter for their season finale.
Tell me how it is, Emma. Tell me how you really feel about it.
Disgusted.
All right,
Putting the map.
I get it. She's disgusted. So because you were just asking, so look, this is next week, right? So lesson 32 next week. So next week it's review, and then in class, the lessons are real abbreviated. It's mostly going to be exam review. And today, if we get through our lesson fast enough, we'll start some exam review. Okay? And then you got lab, and then you got your final.
Why does it say begin lesson 33? Isn't it lesson 31?
No, that was lesson 32 we were just looking at. This would be 33, right? Now, remember in your teacheries, you're gonna have an assignment about pizza.
What?
Yep, you're gonna have an assignment about pizza in teacheries, where you're gonna have to decide how much pizza you want us to get for you before class.
And what flavors?
Hmm?
And what flavors?
Yeah, what kind? There's like a choice of like cheese or pepperoni. We keep it pretty simple. Yep. So that'll be in your teacheries for you to do.
Have you ever tried California kitchen pizza?
Yeah. What kind do you like?
I like the barbecue pizza.
That's a good one.
I am crazy for it. It is delicious.
That's pretty good. There used to be a place, I don't know if it's still there, but it was right outside Helen, Georgia. And my mom and I just kind of stopped there one day on a whim. And they had the most amazing, it was like a garlic, Alfredo, spinach, chicken pizza. And it was so flippin' good. And I've never had a pizza that good anywhere else ever again. It was like a white pizza, you know? Do you like white pizza, like Bianca? I like the white pizza.
No, I prefer I prefer like,
I like them all, really.
I usually like a thicker crust, but California kitchen crust is so good.
Yeah.
Remind me of a saltine cracker.
Yeah.
And if you look at the bottom, it has like all the bubbles like a saltine cracker. Well, it doesn't taste like a saltine cracker, but it kind of has like the.
Yeah, crispy. My favorite, like mainline order last minute pizza, if I have to order from like a common chain, I like the Papa John's garden veggie with thin crust.
Have you ever went to Cooley's Pizza?
I don't think I've been to Cooley's. I liked Fox's. When Fox's was around, they had the best barbecue chicken. I loved that one, and that closed. But I like Grandma's New York style. That's local, and that's really good. They have that, I think it's called Grandma's Special. It's kind of like a margarita pizza, but it has like big globs of mozzarella on top of it. Heck yeah. It's so good.
I think they're coming now.
We ordered pizza this weekend in Cleveland after all the boys had competed in the gymnastics meet. We went home and had pizza and ice cream. It was good fun. Gang.
I have a question for you guys. Has any show ever failed you when it comes to leading up to the season finale or the season finale?
The season finale or the season's finale?
No, I think I got pretty good shows. I have good taste in shows.
Never had any where you get to the finale and you're like, that was stupid.
No.
Oh, well,
I-
Emma
I-
feels cheated right now. She's
What?
extremely unhappy about
The
it.
episode right before the season finale was a filler, and the spinoff has a two-parter for their finale, and I am
What show?
disgusted. NCIS.
NTIS.
Did you ever see that show, This Is Us? It's a family, it's like a kind of like a mixed family, like a blended family. Anyway, there were some adopted kids and anyway, the dad in the show was dead. Like you knew that from the season because all the flashbacks the dad was in and they, you know, when you flash forward or current, whatever, he was dead. We went 2 seasons with that or I think it was 2. And they never told us how Jack died. And Jason got so disgusted with it. He's like, they are playing with me and refused to watch it ever again. He's like, they won't tell me how Jack died. I'm
no.
done.
No,
When
you
Gibbs-
let me down. You
Yeah.
let me down.
When Gibbs left the NCIS, oh, my brother hasn't watched it.
Oh
I
my.
still watch it. I enjoy it. It's something that I've been watching with my grandma for years.
Aha.
There was a game show called Survive the Raft.
Mm-hmm.
Me and Lewis got so mad because the best player got like voted off by some idiot.
Oh.
Yeah.
So think about you guys before you got here this morning, because this was funny. A friend of mine from high school shared like a meme and it said something like public school teachers, it's time for you to quit and go homeschool 10 kids, somebody else's 10 kids, and make $130,000 a year. And I'm like, so my friend tagged me and she's like, is this accurate? I'm like, well, those salaries are not accurate. And somebody else had commented and they're like, sure, teachers pay for supplies, but who pays for the other supplies? Like, who pays for the janitor and who pays for the desks? And I came back and I'm like, desks? We don't have desks. So I had to explain it to her. I'm like, you don't pick public school and try and replicate it in somebody else's house. People don't get it. So
No, you just,
I said, I got 22 kids who come and flop down on my couch. Yes.
I'm gladly happy using my
Yes.
house as a desk.
Yeah,
I
there
actually
you go.
work This way.
Yeah.
Sit on a comfy chair.
Well, I told her, I was like, I tried to answer her questions honestly and be like, cause she's like, who's the janitor? I'm like, I'm the janitor. And I said,
You solved it.
some people, there you go. I said, some people, might be prevented because of lack of space, but we make it work. We make it work, right, gang?
Yeah.
Yeah. Are you ready for your lesson here before we're gonna do a little bit of exam review if we have time? Yes, Mr. Lewis?
I've heard of that.
All right, we are ready. Now, could you bring a hatchet to public school? No. Now, what did you bring a hatchet for?
There's a hammer part of the hatchet, so we're gonna use that.
For what?
The hammer and the
So
nail.
you couldn't bring
To
it.
build your Rube Goldberg machine, or would you be doing that at school with a hatchet? At a public school? Oh,
Awesome final project as a good goal.
thank you. I'm glad you like it.
It's fun. Our zip line is awesome.
Yeah, your zip line is awesome. I'm very excited.
Zip line is so cool. We've come up with our teams here. What's your
Come up is not a.
So
word.
we don't know.
Came up.
You word.
All right, do you want to have time for some final exam review?
Yeah.
All right, then let's roll. Okay, you ready? Let's do it, people. All righty, so, and hopefully it won't rain on us too hard today. So in learning about chemical reactions, it's important to remember this law. Matter is never what? Created nor destroyed. What happens to it? It only changes form. So we call that the law of conservation of matter, right? You're gonna want to remember that. It might be on your final. All right, so then we say that, hello, click there. Matter is anything that has mass and takes up space. Carlos, are you holding matter in your hand? Yes, Nico is holding matter. Am I holding matter in my hand?
Yes.
Yes, my hand is not empty, is it? I'm holding air, right? Air is matter, gas is matter.
Touch the air.
So this law applies to chemical reactions as well. In a chemical reaction, what else is neither created nor destroyed? We got matter. What else, Eunice?
Energy.
Not heat. Huh?
Mass.
Yeah, girl, mass. All right, mass is never created nor destroyed. So that is going to be the law of conservation of mass. We have energy too. Now, energy is going to be conserved and it's going to change form, and you'll definitely see it in a lot of chemical reactions. And you might see it, one of those common ways you'll see it is in a change in temperature. That's where your heat's coming in. Because remember, what's the definition of temperature? Do you remember? No, heat's the transfer of energy. Do you remember?
The feeling on your hand of the like the feeling of your.
That's the heat.
On your hand.
Heat's the transfer of the energy. It's not transfer.
Oh, like how, like.
The temperature is the
Like-
sum of all the energy of all the particles moving. You with me, guys, over on the couch?
Yes.
Temperature is the sum of the energy of the moving particles within matter. So if the particles move faster, then your temperature is going to go up or down. Up, right. Okay, good. All right. So this would be your mass. All right. So why do chemicals react? We only have one video for today. It is a blob. He's got a fire. He's got a bonfire blob. Let's see. We do love some TEDx, don't we?
It's the last.
When your bananas falling on top, your utensils have rusted, you trip and pour all of your baking soda into the vinegar jug, and then your oven explodes. My friend, you and your chemical reactions have fallen victim to enthalpy and entropy, and boy, are they forces to be reckoned with. Now your reactants are all products. So what are these E words, and what's their big idea? Let's start with enthalpy, an increase or decrease of energy during a chemical reaction. Every molecule has a certain amount of chemical potential energy stored within the bonds between its atoms. Chemicals with more energy are less stable and thus more likely to react. Let's visualize the energy flow in a reaction, the combustion of hydrogen and oxygen, by playing a round of crazy golf. Our goal is to get a ball, the reactant, up a small rise, and down the other, much steeper slope. Where the hill goes up, we need to add energy to the ball, and where it goes down, the ball releases energy into its surroundings. The whole represents the product, or result of the reaction. When the reaction period ends, the ball is inside the hole, and we have our product, water. This, like when our oven exploded, is an exothermic reaction, meaning that the chemical's final energy is less than its starting energy, and the difference has been added to the surrounding environment as light and heat. We can also play out the opposite type of reaction, an endothermic reaction, where the final energy is greater than the starting energy. That's what we were trying to achieve by baking our cake. The added heat from the oven would change the chemical structure of the proteins in the eggs and various compounds in the butter. So that's endothermic.
Don't worry about it.
As you might suspect, exothermic reactions are more likely to happen than endothermic ones because they require less energy to occur. But there's another independent factor that can make reactions happen: entropy. Entropy measures a chemical's randomness. Here's an enormous pyramid of golf balls. Its ordered structure means it has low entropy. However, when it collapses, we have chaos everywhere, balls bouncing high and wide, so much so that some even go over the hill. This shift to instability, or higher entropy, can allow reactions to happen. As with the golf balls, in actual chemicals, this transition from structure to disorder gets some reactants past the hump and lets them start a reaction. You can see both enthalpy and entropy at play when you go to light a campfire to cook dinner. Your match has enough energy to activate the exothermic reaction of combustion, converting the high energy combustible material in the wood to lower energy carbon dioxide and water. Entropy also increases and helps the reaction along because the new organized log of wood is now converted into randomly moving water vapor and carbon dioxide. The energy shed by this exothermic reaction powers the endothermic reaction of cooking your dinner. Bon appetit.
We'll do a lot more about entropy and enthalpy next year, but that is why chemical reactions take place. So what is either broken or formed in a chemical reaction? Do you know, Eunice?
Chemical bonds.
Chemical bonds. Okay, this is what's either broken or formed. All right, now, breaking bonds requires energy, but forming bonds releases energy. So you have to it seems a little counterintuitive, but you have to use energy to break a bond. Like you'd have to use energy to break a stick, but you'd think you'd have to use something to put things together. But when you put chemicals together and you have chemical bonds forming, it's going to release energy. Okay. Now, if energy is absorbed in a reaction versus it's released in a reaction, what do we call type of reaction is it when energy is released? You know, Emma? Yeah. Yeah, you're on the right track. Okay. So, yes. So, in energy, in this case, we're talking about energy in the form of heat. So, energy is absorbed by an action. It's endothermic. And when it is released in a reaction, it's going to be exothermic. Okay. Endothermic reactions feel colder than their surroundings. Exothermic reactions feel warmer. Okay, have you ever had one of those chemical ice packs that like when you get hurt, you pop it, it's got a bubble inside and you pop it and then you shake it, it gets really cold. So what kind of reaction is that one?
Endothermic.
Endothermic because it feels colder than the surroundings, right? And so we know that energy is being absorbed. So it's taking in energy from in that reaction and it's making itself feel colder than the surroundings. Yes.
Another good example is like one of those balloons in a package and then you hit it and then it blows up and then you shake it
Yeah,
and it feels kind of cold.
that's the ones we're talking about. Yeah, those little ice packs. They're
But
like,
they're not ice packs, they're just like little balloons.
oh, little balloons. Okay. Uh-huh.
Have you seen those shorts where you bang the really cold water and it turns into ice?
Yes. Yeah, we're gonna do that next year. Mhm. That's totally doable. It's really neat. It has to do with crystalline structure formation. So have you ever seen the opposite kind of packet? Not the ice packet, but the kind you use like hand warmers when you go skiing.
You bang them on the table.
And then what
put 'em in
happens?
your pockets.
What
They
happens
beat
to 'em?
up.
They get nice and
Because of
warm,
the
right?
gunpowder.
Yes, so we know that they are releasing energy and that energy is being released in the form of heat. Okay, all right, now let's have a look here. So a reactant, you guys paying attention over there on the couch? All right, a reactant is the substance that undergoes a chemical change. And it's located, when you're looking at a chemical reaction, what side of the arrow is it on? Is it gonna be on the right or the left? The right?
Right now.
What do we think? Lewis, Lewis, you want to get, Carlos has got it. It's gonna be on the left. So it looks like this. So if your reactants are on the left and your products are on the right. Now, when you write a math problem, if you have an equal sign in the middle, it usually doesn't matter whether you've got, you know, the answer you were trying to get on the right or the left, right? Because equals is equal. But this is not equals. The arrow means yields. Okay? So it's saying, the reactants went up. So you need the reactants first. So the way you remember this is you think about it like you read. You need reactants first and they produce products. And you read from left to right. So this makes sense, right? At least in English, we read from left to right. So if those are the reactants, then the products are what is formed in a chemical reaction. What side of the arrow are the products on?
Right.
We're on the right. Okay.
That is
So-
the right answer.
They look like that.
I
Reactants,
can't really tell
Yield.
the left from right.
products. You know the trick, right? Makes an L.
Oh.
Your left hand makes an L when you put it out in front of you.
I just go R. My dad told me R for scar.
Oh,
Scar on the right hand.
R for scar on the, that works, whatever works. All right, so let's look at a chemical equation. Let's break it down and see what it looks like. So these are the chemicals we're going to use in this reaction. We're going to use carbon, hydrogen, and oxygen. All right, there they are. That's all that's here. Carbon, hydrogen, and oxygen is the only elements we're messing with in this particular equation, just to show you what it looks like, okay? Now, coefficients tell us how many molecules of each of these substances exist. Where does a coefficient go in a chemical reaction? Right underneath, to the side, right, to the left. So they go in front. So how many carbon monoxide do we have? Right now it's carbon monoxide, right? Because there's CO. All right. Well, we'll come back to it. It's going to change in a minute. Subscripts tell how many elements of each substance are in each molecule. So where do those go? You had that, Nico. Where do they go? Under, yeah, kind of under, like that. Those are called subscripts. Now, in chemistry, we do have superscripts that we use for things like ionic charge, but we're not gonna mess with that right now, okay? So, let me ask you, in this first molecule, how many molecules do we have of CO2? 6. Do you know what CO2 is?
Carbon dioxide.
Carbon dioxide, because now we know that's a 2. We didn't have that at first. It was just CO, right? That was carbon monoxide. Now it's carbon dioxide. How many oxygens do we have in that? How many oxygen do we have in just this first unit?
2.
Not 2.
No,
Look at it.
18.
We have 2 in each molecule. We have 6 we have 12. We have 2 in each molecule.
2 times 6.
And 6, there you go. So we have 12 oxygens there, just in that first one. So we have 6 carbon dioxide plus 6 what?
Carbon.
No, what's 8?
Hydrogen.
Oxygen.
6 H2O. That's
Yeah.
6 molecules of what?
Six,
H2O.
What's H2O?
Hydrogen.
Oxygen, water.
Water. 6 molecules of carbon dioxide with 6 molecules of water.
H2O.
Now, what is C6H12O6? Anybody know? It's a sugar. It's a
brown sugar?
specific sugar.
Castor.
It's clue. Okay, and then look at the 6O2. What's that? That's an easy one.
H2O, CO2.
No, this is a six
Oxygen.
oxygen.
Okay.
How many oxygens are in each molecule? Right here.
Two.
2 oxygens. So we have how many total?
Wow.
12, right? Okay, so here's what we have. That's yields, right? So we would read it like this: 6 molecules of carbon dioxide plus 6 molecules of water. And in this case, our energy is going to come in the form of sunlight, okay? And it's going to yield 1 molecule of glucose, which is a sugar, plus 6 molecules of oxygen. Yes,
Is this like how plants grow?
you're close. You're real. Yeah, you are partly yes. And the bottom one is going to read a little differently. 1 molecule of glucose plus 6 molecules of oxygen yields, what's this next one? 6 molecules of
Carbon dioxide.
plus what?
6 molecules of water.
Okay, what do you notice about these 2 reactions? The energy in this case is going to be on this end,
Yes.
and it's going to be in the form of ATP. But what do you notice about these 2 reactions?
They're interchangeable? Or like
They're-
you can. Yeah.
Reversed,
Yeah.
right? Okay, no, you were right, Emma. That first one, how do plants make energy? How do plants?
Photosynthesis.
That's photosynthesis. That first reaction is photosynthesis. Do you know what the opposite of photosynthesis is? Anybody know?
We kill.
Not which. That's a good question. That's a great answer. So what you're looking at here is, these are our reactants. I'll tell you in a minute what the answer is, right? These are our products, but they're the reverse of each other. So energy went in this one, right? It came in right there in the form of sunlight. Energy went out in this one. Okay, so we know that that second one is exothermic. All right, let's think about it. This first one we said was photosynthesis. What's the opposite? All right, let me ask you this. Okay, real close. What was this first? What was this big molecule? It's a
Sugar.
carbohydrate. Yeah, it's glucose. It's sugar. So sugar and oxygen. Who uses sugar and oxygen to make energy?
Humans.
Humans do. Yeah, most animals do. Okay. And what do we exhale?
Oxygen.
And
Oxygen.
yeah, we exhale carbon dioxide and water. So what, those are our waste products. So this action, this is aerobic cellular respiration.
Never would have guessed
This
that.
is how your body makes energy. This is how your body processes the energy it gets when you eat, and you eat sugar, and then you exhale carbon dioxide. That's what happened to the sugar. You see it? All right, so that's what happens inside your body. So we can describe chemical reactions. Because chemical reactions often involve large numbers of particles, chemists use a different unit to measure amounts. What's the name of that unit? Do we know? It's a mole. See the mole? Any cute mole? 6.02 times 10 to the 23rd. It's a big number. Okay. In chemical reactions, the mass of a what can be calculated by using a balanced chemical equation in molar mass. Do we know?
Nope.
It's going to be your reactant or your product. You can calculate it by using these formulas, and we're going to be doing this next year. It's going to be fun. Okay, signs of chemical reactions. So how do you know that a chemical reaction has taken place? All right, here's how you know. Here are some ways you can tell. All right, so first,
Formation of
if we started and they were all clear, and we added a little bit of something to each one of those, not dye, but a chemical. Now we have all these different colors. What would be a clue here that a chemical changes? Color change is right. Change in color is a clue of a chemical reaction having taken place. All right, now keep that in mind. Why do your shoes stink? Yes, odor. Okay, production of an odor is a clue that a chemical reaction is taking place. Why do dead things stink?
Because they're
They're
rotting.
gases.
Yeah, they're releasing gases, but where are the gases coming from?
Their feet.
Just
No, I'm kidding.
From the chemical reaction of their cells breaking down and the microbes start
Oh,
eating them and.
That's what happens when you have like a heart attack and your body starts decomposing.
Well, yeah, if it kills you, hopefully if the heart attack doesn't kill you, you won't decompose. 'Cause
Yeah.
That would be really gross.
All the skeletons.
Yep.
Oh, I
So
saw a movie called Spy. This guy's throat started decomposing.
that's disgusting.
Yeah.
All right, how about this? What's happening here?
Chemical reaction.
So that's not just the color, because now this is, oh,
I saw
so this one's a little trickier. So this one
it.
is
Change of matter.
formation of a precipitate. Remember, I think you did this, didn't you do this in a lab where you had something make a, like, turn cloudy? Yeah, that was earlier, right? Yeah, you drip something in a test tube and then the substance.
Magnesium chloride.
There it was. Yeah, that's right. Couldn't remember what it was. We've done so many labs and it turned
I
the
knew
substance
it was
cloudy.
something.
It's cloudy because there's solid particulate in it now, which we call a precipitate. Okay, here's another one. What's happening there? Those are bubbles.
Changing temperature.
And then carbon dioxidation.
Doesn't have to be carbon dioxide. What are bubbles?
Changing
Particles?
volumes.
What's inside the
Air.
bubble? Gas, right? All right, so we're talking here about evolution of a gas. Some chemical reactions are going to produce a gas. They talked in that video about vinegar and baking soda. Anybody ever, you've done that, right? Everybody's
Yeah,
done that.
that's actually the ending thing to our Rube Goldberg.
Oh, cool. And it makes a gas, right? Actually, it's carbon dioxide that it creates. Do you know that if you do that carefully enough and you catch all of that carbon dioxide, you can pour it over a candle flame, the gas, you can pour it over a candle flame and it'll put the candle flame out because it'll snuff out the oxygen. You can actually pour gas over the candle. It'll put it out.
Because fire needs
Really neat.
oxygen.
Yep. And next year, one thing we're gonna do is we're gonna separate water into hydrogen and oxygen. And then you're gonna take a match that you will have blown out, but it's still kind of glowing, and you put it over the test tube that has oxygen in it, and it goes, and it makes this loud noise and it flashes for a second because fire needs oxygen, right? It's combustion. It's pretty cool. All right, what would this one be?
Changing.
There you go. Change in temperature. So we were talking about those little packs that you use to warm up your hands or ice packs. That's a great example. All right, what about this?
Those are glow sticks.
Yeah, they are. So what do they produce?
Light.
Light. Yes, production of light.
We said that.
Crunch, crunch, right? Yeah.
It makes like a.
I had a friend who ate part of the glow stick once. She had to go to the hospital.
Would not recommend that. That sounds disgusting. But yes, production of light is another sign of a chemical reaction. All right, now. How about this one?
Fireworks.
Fireworks.
That's
That's
like
like
what?
Hmm?
chemical reactions.
It's a chemical reaction. In this case,
Powder.
sound is what we're going for.
Oh.
You ever, you hear a firework and it explodes, right? It goes bang. Why is it doing that? What's happening? Why is it making that bang sound?
Because of the
Yeah,
collision. Because of the speed when it hits,
Gunpowder.
When it
When it
explodes, yeah, there's a combustion reaction
it's
going
like
on,
a
right?
big bomb fun.
Yeah, it's a combustion reaction. So something's, catching fire and then exploding, right? You go boom. And that's because it's hitting the air around it, right? It's causing sound wave. Remember those longitudinal sound waves? Right? Same thing. All right. And then, what might this one be?
Lightning.
It's lightning.
Energy.
Oh,
production.
energy.
Energy, yeah, we're talking about electrical energy in particular. Very good. So sometimes chemical reactions can absorb or release electrical energy. That's really cool. So those are our examples of how you can tell. All right, now we have different types of reactions here. We have synthesis reactions, which is when two or more substances combine, and an example would be like sodium and chloride making sodium chloride, which is table salt, right? That's a synthesis. Synthesize means to put together, right? Like to create something new, right? We also have decomposition. So you guys okay? So if synthesis is putting things together to make a new thing, then decomposition is gonna be what?
Taking stuff apart.
Taking stuff apart.
Like hydrogen.
Yes, so a great example here is carbonic acid, which is an ingredient in your soda, your soft drinks. and a decomposition reaction takes place.
It's like
I
butter,
don't-
like.
Right, when you're-
carbonated.
It breaks it down into water and carbon dioxide and you get fizzy, right?
My soft drinks are banned in my.
And then we have combustion. This is what we were talking about with the fireworks.
The example is
Mhm.
just anytime you burn something.
Anytime you burn something. So let me ask you this, is starting the fire with a wood, a chemical reaction?
Yeah.
Yes,
Because
it
it
is.
changes the form of the wood.
Right, it does. It's changing the substance into another substance. It's turning the wood into like carbon. And then,
Ashes.
yes, and then
Which is
energy is
fire.
released in the form of heat. Then you have these things called single replacement. So this is when you're taking one element out and replacing it with a different element. So for example, potassium reacts with water and it forms a colorless compound called potassium hydroxide. So we basically, in this case, we've taken out one of those hydrogens and put a potassium in and we get KOH. All right. And then you have something called double replacement. So this is when you have two compounds reacting, you have positive ions, which are cations, and negative ions, which are anions, and they switch places. So a reaction example would be sodium bicarbonate. What's sodium bicarbonate? Common name. It's baking soda.
Baking.
What's acetic acid common name?
Vinegar.
Vinegar, right? And
I was ready for
it forms a salt, which is sodium acetate plus carbon dioxide gas and water. So when you do your reaction at the end of your Rube Goldberg machine, Darcy, you're not just producing the gas, you're also producing a salt. Anytime you put a base and an acid together, you typically get a gas, a salt, and water. That's just kind of a general rule. Yes, ma'am.
I thought we had to end our machine with like the sounding of the.
Yeah, you do have to end it with the sound of the cymbals. I think she's meaning it's towards the end, right? The last thing is the sounding of the cymbals, ching ching, the cymbals that are in your bag.
Yeah,
Yeah.
like when it explodes.
Oh, it's gonna be what does it when it explodes. Got it. All right. So scientists classify certain chemical reactions as transfers of what? What's transferring? What's actually transferring when chemical bonds form?
Jet.
Electrons. Remember, it's those electrons floating around. So that's how we're getting there. All right, so you can measure the rate. And you can, what's rate mean? We did this in the first quarter. Rate is kind of like what?
How fast you're.
Yeah, kind of like your speed, how fast you're going. So the rate of a reaction, by examining the ratio between the amount of a substance or products formed and the time it took to produce them. So it's the amount and time. Whereas when we did rate at the beginning of the year, we were doing distance and time, right? In this case, we're doing amount and time, but it's over time. And you can measure them by mass per unit volume or per unit of time, right? So what were you gonna ask, Darcy?
I was gonna ask, I've been wondering all year, did you paint that?
Which? This?
Mm-hmm.
This? Any of this? No.
The cabinet.
No, I didn't paint it. It's contact paper.
Oh.
It's really cool. I found screaming yellow and bright orange. It was perfect. So factors that affect reaction rates. Let me ask you this. If you want to increase the rate, the speed of a chemical reaction, how might you do it? What might you do? You know? So what you're trying to do is you're trying to lower what we call activation energy. Remember when he hit the golf balls up the hill and then they got to the top and they went over? That top of the hill, that crest of the hill is what you call your activation energy, okay? If you can lower the hill, right. If you can lower the hill and make it less tall, you don't have to use as much energy to get the ball up, right? So things you can do to lower that hill, for example, you can have a higher concentration of reactants. That's going to be a better, faster reaction. You can also temperature here in particular, typically increasing a temperature is going to make a chemical reaction take place faster, typically increasing.
There's these golf balls that make a ginormous sound when you hit them.
Mm-hmm.
And-
Gunpowder.
And they're filled with gunpowder.
Fun.
And the activation thing,
Yeah.
it went through the golf ball
Oh, wow.
and it flew so far.
So it's got black powder in it. That's pretty neat. What were you going to
Yeah,
say?
you know those little poppets that you like throw on the.
Yes.
So one time, my grandpa got one that were red
Mhm.
and they're about this long.
Ooh,
And when you threw them on the ground, it sounded like a gun shot.
those are cool.
They were awesome.
In commenting on your golf balls with black powder, I recently saw a device that's used for putting nails through masonry, like concrete.
Yeah.
And it used a 22 milliliter round put inside of this little apparatus, and then you hit the top of it with a hammer and it hits the back of the bullet just like a gun hammer would. And it uses that propulsion to fire the nail through the concrete. It's really cool tool, but man, be careful with that, right?
My friend once told me that you can make a flamethrower out of a PVC pipe bug spray and
You can,
I
yeah.
can make a bomb out of a Febreze can and some string.
They're scary, Darcy. All right, so back over here, we can increase we can decrease our activation energy and increase our reaction rate by concentrating our reactants, increasing our temperature, also the physical state of the reactant. Sometimes it's easier if they're in a liquid state or in a solution versus being a solid or being a gas. And the presence and concentration and physical form of a catalyst. Okay, a catalyst is specifically meant to, it's another chemical you're going to involve, and its entire job is to lower that reaction rate. I mean, the activation energy, so that your reaction rate is faster. Okay. And an inhibitor would do the opposite. And sometimes light can increase the rate of a chemical reaction. Right, so let's talk about equilibrium. What's equilibrium mean? What's the word mean? What's it mean, Lewis? Yeah, stability, balance, right? So when a physical change does not go to completion, a physical equilibrium is established between the forward and reverse changes. Okay, so reactions that can go forward can go backward. Remember when we looked at photosynthesis and cellular respiration a minute ago? They were opposite. So it's the same chemicals. It can go one direction or it can go the other direction, right? So when a chemical reaction does not go to completion, this is what we call a chemical equilibrium. It's established between forward and reverse. So when a change is introduced to a system in equilibrium, the equilibrium shifts in the direction that relieves the change. So here's what you need to know about equilibrium for this year. We'll get into it next year. But for this year, what you need to know about equilibrium is that all things really like equilibrium. They really don't like to be out of equilibrium. Equilibrium is where we want to be. So in particular, concentrations of chemicals, like if you have a barrier or a membrane, for example, they want to be the same on both sides. You don't want to have like a heavy concentration on this side and a really dilute one on this side. If that membrane allows things to pass through it, they will pass through it until they're both equal. And that's very important because our bodies use equilibrium for us to function. And if we're not at equilibrium, our bodies will do certain things to put us at equilibrium. So here's an example, okay? You won't forget this one because it's a crazy example. So say you have to go get a test done where they need to look inside your intestines. Anybody know anybody who's had like a colonoscopy or anything like that, or like an IVP? Yeah. What do you have to do beforehand? You have to drink a solution. Yeah, and it cleans out your whole body so they can see inside you. What do you think is in that solution?
Something that.
Laxative.
It acts as a laxative, but here's why. It's usually a salt, okay? And it's a
Dries out
heavy,
your intestines.
it doesn't dry it out. What it does is the salt goes into your intestines as you drink it, right? It goes through your digestive tract and it gets into your intestines. And the job of your large intestine is to balance how much water goes in so that you're not getting rid of too much water, and you also don't have not enough water that you're getting rid of. So when you put a lot of salt on the inside of your large intestine, what's it gonna do to get equilibrium? What do you think? How's it gonna balance it out?
and get rid of
You got tons of salt on this side of the membrane of the intestine. It's gonna pull water from the rest of your body into your intestine to balance out the salt. So what happens when your intestines get full with tons of water? You're gonna be going to the bathroom a lot. So that's a great example of where we use equilibrium in like the medical field. You have to have that equilibrium, and we force it in order to like clean out intestines. All right, so carbon and nuclear chemistry. This is a quick little preview. We're just gonna dance over it. You guys with me over there?
Yeah.
All right.
check something here. I think I dropped my water bottle.
Okay, good look. So some elements naturally change into different elements. For example, for an element to change into a different element, it must change the number of protons in its nucleus. We know this, right? Because the number of protons determines what an atom is. You can have a different number of neutrons, and what are you going to be? What is it if an atom has a different number of neutrons?
The amount of protons gonna be the same.
Starts with an I. What's it called?
Ion.
Not an ion.
Isotope.
Isotope. Good job. Ions have a different number of what? Ions have a different number of electrons. He's got it. Ions have a different number of electrons. Isotopes have a different number of neutrons. But if you have a different number of protons, you have a different element, right? Protons determine what the element is. So some elements will naturally change. You good? So some elements are going to naturally change with time into a different element, which means they're going to have to lose or gain protons. But this only happens to radioactive ones. Where are radioactive elements? Where are they? Down here, right? Right? Here's our uranium. It's these guys right here. Yeah, plutonium. So unstable nuclei of radioisotopes. So radioisotopes mean you have a radioactive element with a different number of neutrons, right? Radioisotopes become stable by emitting charged particles and energy. What charged particles are they emitting if they're changing into a different element? The positive particles or the negative ones?
Negative.
The negative ones are what? Yes. Why, Nico?
Because protons define what.
There you go. You've got it. So this is when one element changes into another. So nuclear energy is released in nuclear reactions. Two types of reactions that release huge amounts of energy are fission and fusion. What's fission mean?
Fission means coming apart.
Yes.
Fusion means coming together.
Good job. Very good. All right. Carbon chemistry. Here's our brief touch of carbon chemistry. You with me, Lewis? Okay. Carbon can combine with itself and with many other elements to form great diversity of compounds. There are millions of things known as carbon compounds. You hear people talk about your carbon footprint. That's why, right? So hydrocarbons are compounds that contain only carbon and hydrogen. They're the simplest form of carbon-based compounds. The smallest hydrocarbons have just one or two carbon atoms, but large hydrocarbons have hundreds. So the size of a hydrocarbon influences its properties. And as a result, some are gases at room temperature, others are liquids, others are solids. And hydrocarbons are generally non-polar. What does non-polar mean?
Non-polar.
Lewis?
Non-polar means they can't be mixed together.
Doesn't have,
Doesn't have.
what's it mean to be polar?
Polar means they can.
They share attract.
Close.
No, they
Steal
steal stuff from each other.
If they can.
Magnetic stuff.
Magnetic is one way to describe polar. Another way is electric. So they don't have a charge on one end. They're not charged particles. They're very neutral, non-polar. And in fact, they tend to repel water. What's a good example of something that repels water? Does not mix with water. What?
Oil.
Oil is a hydrocarbon. There you go. So the classes of saturated hydrocarbons and unsaturated, they're broken down. And that has to do with like how many hydrogens are there. And so the classification is based on the number of bonds between carbon atoms. Carbon is the most important element in living things. Carbon-based compounds in living things are generally called biochemical compounds. What do we call pretty much anything any molecule or substance that comes from or is produced by a living thing and it contains carbon? We have a word for those. Do we know? Starts with an O.
Oxygen.
Oxygen. Organic. Organic. So is wood an organic compound?
Yes.
Is hair an organic compound?
Yes.
Is a rock an organic compound?
Yes.
No.
No. Yes. Yes. No. Yes. Yes. Yes.
What kind of rock are we talking about?
Depends.
Yeah. Is coal an organic compound?
Yes.
Yes. What does coal come from?
It comes from.
Swamp stuff, dinosaurs, right? So, right. But how about granite? Is granite an organic compound?
No.
No. How about quartz?
No.
No. Good guesses. All right. So chemical, all living things need energy. It comes from chemical reactions. Reactions take place within living things that are called biochemical reactions. And the two of the most important are photosynthesis and cellular respiration, which we saw earlier. And we know now that they are reverse processes. So here are examples of carbon compounds. You've got carbohydrates, which are things like sugar and starches. They contain carbohydrate and oxygen, and they're used for energy and structure. You got lipids. These are fats and oils. They contain the same three elements, look there, but they're arranged differently and in different numbers. And this is like cellular membranes, energy storage. Then we have nucleic acids. Where do you find nucleic acids? Do you know, Lewis? Okay, you're close, you're getting there. You're almost what I want to say, yep. What is an example? Yeah, what's an example of a nucleic acid? How about if I told you deoxyribonucleic acid? What is that? That is DNA. Ah, so you have nucleotides. Look, we've now added nitrogen and what's the P? What's the P? Nitrogen and? Nope, phosphorus. And this is for storage, transmission, genetic information. Then we have proteins, which are made of amino acids. And look, we don't have phosphorus here, but we have carbon, hydrogen, oxygen, nitrogen. And these are enzymes, channels, and structures. So the most important elements in living things are, you ready? Carbon,
Oxygen.
hydrogen, nitrogen, oxygen, phosphorus, and what do you think the last one might be?
Oh, wait.
We've, you're close. We've seen all of these already in our examples. It's going to be sulfur. Yes, there are some organisms that do not do our typical type of respiration or photosynthesis. They actually live off of sulfur. Those are usually guys that are way at the bottom of the ocean where they get no light, and they're sulfur-based life forms, which is pretty interesting. We remember this by saying SNOPs. CHNOPS, SNOPs. These are our most common elements in all living things, okay? Then you have a carbon cycle, and it goes like this, just so you know. We're whipping through these. We have photosynthesis, respiration by plants. That's how it happens. The little rabbit ate the little plant. It's a scary looking rabbit. And then respiration by animals. So he's breathing. He's making carbon dioxide in the air. Whoops, he dies. Now what's he going to do when he dies? You get fossil fuels from him millions of years later, like that coal, right? And then lastly, in this, we have combustion. So this is the carbon cycle. We have a carbon cycle. We have a nitrogen cycle. We have lots of different cycles. We have a water cycle, right? But this is carbon cycle. So when they talk about carbon footprint, they're talking about what waste are you leaving behind, right? That's what they talk about. That's what it means. So that's that. And it is exactly time for lab. And it looks like it isn't raining at the moment. So I do not want to cut into your time. I want you to be able to get out there and do your stuff. So, hey guys, come on in. So wait a second before you go running. Let me make sure. It's there. You have a copy of it. So yeah.
Say,
I think we should think of the various and made up elements.
Great. All right, and make sure everybody's here. No, not unless you want to take notes.
If I ever discover an element, I'm going to
Lou's also
potassium infinite.
Potassium infinite. That was funny.
Luscious.
All right, gang, listen up real quick. I want to give you as much time as possible to get out there and work today. It's wet, so please deal with your shoes accordingly before you come marching back in here. Also, please be sure that when you're using your tools and equipment that you're responsible with them and you lay them down like on paper or on your picnic blanket and not in the dirt and the mud, because that will destroy them. That's gross. And nobody else can use them because they'll get rusty, whatever. Anything that you get wet that you need to dry off before you come in, I'm going to bring out some paper towels just in case. Okay. Lastly, as long as it doesn't thunder, you're free to be out there. If it starts thundering, we got to change and come back in, and you're just going to have to figure out what to do. Okay. Are we all good? Are we all ready? Does anyone have any questions or need anything after last week? You're ready to go? All right. Hit it. I'll come out with you. We're going to do it. It's going to be good.
Why is everyone going now?
They're getting their stuff. Yo, you. Congratulations.
How are you? Also, so, Rio Valley gets highest solar power.
Doesn't exist on the Xbox Online.
It's hard, at the meet, that means that's interact, because it uses me for this source. One thing, yeah, I get a minute. But. I'm sorry. Cause I'm not taking food. One guy did it. Yes, one guy did a food way. Perfectly.
So give them a small one.
We're all like.
It's small.
Yeah, it's one already. So anyway, we'll look at unbound. Other guys that competed in the before, they're really younger. It looked like, our level 10's going, huh? Cause he's going to Daytona, but his brother's competing, so he came, he was so confused. He's like, what is going on? I'm like, I don't know, but I don't like it, so. I think the first place guy had a 68.6 for his own, you know what I mean? I'm like, what are you doing? This is craziness. All right.
All the wrenches on the floor.
Oh, well, could you put those on the table? You know, when I need to get them. Thank you, sweetie. All right, off you go. Go do your thing. I'm coming out with you. There you go. Do it. Do it, do it. I boo. You want to come outside with mommy and kids? Let's go. Let's go, my friend. Hold on, wait. Yes. Let's do it, Oz. Let's do it, Oz. You want here?
true. Accurate. That's what happens. Hold on, boo-boo, just a good boy. Yes, I know, you're just getting something to bear down on and a pen. Then I'm going right back out. I need to do this. Oh, I need to kill this lesson. It's still,
I bet I work
See?
with the same tennis shoes, so I can flip them off.
there you go.